Yes, you know, in the IWST, I don't know when, there will be a presentation of a guy that is using converting images to music. It's really strange, but you can enjoy it somehow. The last talk today, so if you are into strange music, you can enjoy it.
Okay, hi guys, how are you doing today? This is about music, so if you want to dance, you can dance, otherwise you can move the feet, just a little bit, hold the head, this way. Well, this project is named Let It Be, and it's about generating music from Smalltalk code. A couple of words about me. My name is Guillermo Amaral. And I work for Petroviar. The company previously had named Sister Systems. I'm also part of the Bee team, and I'm not a musician, not a composer, sadly. The thing is that I started this project when I saw this work from this guy, Larry Guan, which is about deriving music from pictures. What he did was basically to apply filters to paintings, and then based on the information coming from those filters, he derived music. So for instance, this is the music coming from this picture. Very interesting work. So I then started to search more words in the same line, and I found this job that it's, believe me, amazing. This girl, Hannah Davis, wrote a program which derived music from books, textbooks. What she did basically was to first analyze the textbook chapter by chapter, extracting the main emotions in each chapter, and then based on those emotions, she created, or the system created, a composition aimed at transmitting the same emotions. So for instance, this is the music resulting from this book, Peter Pan. So then I asked myself, I wonder, what if I generate music from my code? And more important, what aspects of my code would I like to reflect, right? So the basic idea is that the code that looks good should sound good. The ugly code or bad code should sound probably not so good. The thing is that I was telling this idea to one of my friends. Yeah. And then I suddenly remember this famous scene when Marty McFly, this is Back to the Future 1, Marty McFly is playing in the party where his parents are meant to kiss for the first time, and he's playing well. But then George McFly has some delays in kissing Marty's mother, Lorraine. So Marty basically starts to disappear. And then he starts playing. Do you see? By the way, this face, perhaps is the face when you look that cold. A couple of minutes after, Marty recovers. George McFly finally kisses Lorraine, and then Marty recovers, and then he starts playing well again. So that's the idea. This scene really depicts what I try to do. Well, sorry. Okay. So this idea is inserted in a field known as algorithmic composition, which basically deals with applying formal procedures to the process of musical composition, right? And just to give you a glimpse of what it is, if one thinks about an algorithm as just a list of steps, well, the thing is that it's been present almost throughout all our history. I mean, from ancient Greeks, who were the first guys in introducing formalisms to music. And it's plentiful of examples. I don't have the time to stop in each of them, but this is one of the most famous examples, which is known as a dice game, usually attributed to Mozart, in which the composer basically picks one measure from a set of pre-composed measures by rolling the dice. And that way, the composer introduces randomness into his compositions. And this was actually used, and probably the result was a family or versions of the same composition, but the thing is that it was used for real compositions. Then, when the computer appeared, of course, these techniques increased. I mean, there was a lot of people doing stuff in the same line. Particularly, this guy, Lettern Hiller, was one of the first in writing a program that produced a composition entirely. I mean, the machine, the computer, generated a composition. And the work he did, he did it with a mathematician. I mean, Lettern Hiller was a chemist and a composer, and he worked with this mathematician named Isaacson. And this is, if you listen this composition entitled, you cannot believe that it was composed by a computer just by applying some rules. It's outstanding. Well, of course, there is here Yannis Xenakis, which was another composer. I think he was an engineer also, who introduced some formalisms coming from physics to music. But this is just a classification I did. There are some techniques that are used to assist the composer, the human composer, while other techniques consist on just using the computer to produce compositions. There are some that use deterministic processes, while others use stochastic processes. There are some that start from scratch, meaning that they have no information to start with, and then there are other techniques that consist on training the computer, for instance, in a given style, so the computer is aimed at producing composition of the same style. And then this is what I did, right? Start from a given input. I mean, take any sort of information as an input and then derive music from it. This is just a bunch of examples of the techniques. They go from AA to learning systems, evolutionary methods, Markov chains, and these techniques are not used isolated. They are combined. And I was interested, I am interested in the whole thing, but in particular in this project I was interested in this kind of techniques that starts from something, numbers, whatever, and then generate music from the input. So what I did, I had no support for MIDI in my Bee image, so I implemented a MIDI API, a bunch of FFI calls, and then based on it, as I think every Smalltalker does. I created many things such as files, tracks, events, or and then my own MIDI player, because I'm a Smalltalker, I want a MIDI player inside Smalltalk. And then I implemented a MIDI parser to read and play back files. And I had some error that Jan helped me yesterday to fix. And then when I had the chance to extract some sounds of my computer, or of my computer, what I did was to dump all my basic and modest knowledge about music, such as scales, notes, chords, and then some other stuff such as scores or music sheets, things more related to the compositional work. And then the composer, guy who produces composition, and then some other objects to generate notes and chords in a string pattern way. So what I can do now is to show you a couple of examples. This is a Bee Smalltalk browser, and here what I have is the hierarchy of composers. And for instance, the first thing I did was to implement a couple of basic composers. This is the text-inspired composer, meaning that the input of this guy is a text. So for instance, I have here an example, I guess. Okay, here what I do is to create a composer. I tell it the text that it has to use. Okay. Better? Okay, so what this guy does is basically he maps letters into notes in a given key. So this is the composition resulting from this text. And here I have some information about the composition. But the thing is that this guy is a sort of dumb composer in the sense that it only maps notes in letters into notes. The same happens with this guy. This guy takes a number, digits of a number, and then just applies a map for the melody. For the harmony, what he does is basically plays a chord above each measure depending on the note below, I mean the note in the melody. So for instance, this is so this is quite simple. There is another thing which is the rhythm behind these compositions. I have here another example which is composition based on the first 1,000 digits of the number pi. Okay, it's very interesting. It was not me, it was the computer, right? Okay, so then we'll go back to the presentation here. I started to work with code-inspired composers. So the idea is that these composers take three inputs. Source code could be a method, compiled method, could be a class or a bunch of classes, whatever, project, package. And then they also take as input one metric, a given metric. I used complexity, and a threshold. So the idea is that the metric, if the metric surpasses the threshold, you should, or I should, hear something strange in the composition. But they take several decisions. First, they decide the key, the scale of the composition. And what they do is, first off, they calculate some statistics of a metric of a given code. And then if the metric is, the average of the metric is above the threshold, they use a minor key, a minor scale. Otherwise, otherwise they use a major scale. The idea behind this is that major scales are usually associated to happier compositions. Of course, one might think that a minor scale might be used to produce beautiful composition as well. So, but the thing is that perhaps if you feel sad about what you are listening, you can go and see your code and see what's behind. The tempo is pretty much the same idea. This is a linear function that basically maps the average of the metric in a given range of tempos. So higher tempos are associated to happier things, right? While slower ones perhaps are associated to slower ones. So the idea is the same. If the metric of the code is above the threshold, what you will listen is something dense. And regarding time signature, compositions support several different time signatures, but these guys leave it fixed. Now, going to the melody, how the notes are decided by these guys. I basically explored three ways of generating melody. One was by using the AST. So suppose you have a compiled method, then you have the AST, and then you have some metric, perhaps the complexity, some complexity at the different levels. So for instance, if I take the first level of the AST, and then I apply a map between the numbers and a given scale in terms of degrees, otherwise these composers would be clumping these numbers to a given key. And that's it. What these composers can do is just generate a melody based on the metric of each node, AST node. So that's the first idea I explored. The second idea was to consider bytecodes. Again, if I have, for instance, a compile method, I can have bytecodes, and then I can have the families of bytecodes. So what I can do is to apply, again, a mapping between the types of bytecodes and a given scale. And the idea I had when I did this was to, I thought I could perceive the distribution of the bytecodes from my code, something which is impossible, I think. And then, thanks Valeria, I explored this idea, which is even more simpler idea, which is take into account the size of the compile method. The size tells us something about the complexity, I mean the amount of literals or block closures, and then apply again a mapping between the size and a given scale. So for the rhythm, regarding the rhythm, these guys use Markov chain, first order Markov chain with different motifs, which are kind of short pieces of, short length pieces of music, and the edges or the transitions in this machine, yes, represent the probabilities to jump from one to each other. So motifs that are related have higher probabilities, while are do not. And the idea is that when something wrong is detected, again based on the threshold and the metric, the given metric, these composers change drastically the probabilities of this Markov chain. So the idea is to destroy the rhythm, to destroy the melody, and now we will see what they do with harmony. Harmony can be based basically in two things. One is the note below. I have here a measure, and then this is the note, the G note. So the simplest way is just to generate a triadic chord based on that note. I mean, basically a chord with its root as the note below. The other alternative is to use a chord progression. This is just a sequence of chords, basically. There are many known chord progressions. And then, again, based on the metric and the relationship between the metric and the threshold, chords are altered. Meaning the notes are added to them, and even notes outside the key. So the idea is to produce as much noise as possible when something wrong happens with the code. So this is just, I don't know if you can read it, but this is just the steps of each composer. But I will show you another example. Okay, here I have the bytecode inspired composer. So what I will do here is to create a composer. Then I will tell it that the metric is complexity, the first one is 15, because I know that it's a good number, basically, for this example, using the class string, right? So I will tell it that to produce a composition that I will play. And then takes a couple of minutes, seconds. So here I have the composition, and what you see below is the method, the compile method, followed by the. Do you notice? So this method slash has a complexity above the threshold, which is 15. So if I go now to the string class here, and then I suppose I change this method, okay, what I can do is just to return self. whatever.
Be careful.
Whatever, the complexity is 0, right? So now what I can do is to regenerate the composition and see what happens with that method. Okay, if I play again. It was fixed, right? Thank you. The other alternative was the IST. I will do it with a lower complexity here, lower threshold, sorry. I forgot to put the lyrics of this song, but the idea is the same. So this is how the AST nodes of the method of a class string sounds like. One way.
White code's better. White code's better.
Good question.
No.
I was expecting to hear something odd because the complexity I put was 5.
Let's scroll so we can see the maximum.
Okay.
42.
Yes, perhaps we didn't reach that node yet. But well, finally, the third example is the using the again for class string. This time the size of the method. There, I don't know if you noticed, but something a little bit odd in the harmony happened, right? Again. Okay, that's it. We can go back to the presentation. So this is just the future work. I will like to work more on different things such as genders and such as. And for instance, percussion. Percussion really provides percussion, so why not to try something with percussion? It would be interesting. And different other things. By the end of last year, I was driven with listening to this album. These were the songs. Perhaps, Martin, you remember your favorite one. You are the exception. But now, I'm dreaming with this. Even a concert. First Smalltalk Music Festival. So, that's it. So if you have any question.
I would like to put a bit of history. The first Smalltalk lab in France was in IRCAM. And the first thesis of Pierre Quant was about music composition.
Well, haven't seen that word.
So, because at that time labs were not able to buy US computers, only IRCAM was able to do that. That's why Smalltalk was born in music in France.
Good. Yes.
I really want to write my own music with this. Where can I have that? Is it, in other words, is it available? Are you ready to share your work, or how?
This is free. I mean, the code is available, but the only detail is that it is implemented in Bee Smalltalk. So perhaps when Bee Smalltalk is released, which will be open source. But I can share the most of the stuff, the music framework, so to speak, plus the composers are, I guess, decoupled. Just links with the low-level stuff of MIDI. So if you have your own MIDI support in your image or your Smalltalk, I can give you the code, but we all know that migrating code from one dialect to another requires some work. Yes, more or less. Yes. Yes.
Have you tried to write like a test case or something that plays Happy Birthday?
No, I haven't. I could.
I'd like to mention that music has also been used for debugging. For instance, if you go into infinite loop, then you will go something.
Cool. Yes, well, in fact, this is static, right?
Yeah.
But I thought about generating music from some dynamic runtime. I don't know. It's there's a lot of ideas that arises when you.
Maybe it's easier to catch the wrong code with your own music. I mean, you can put I don't know AC/DC music and just make it wrong when there is a bad code instead of just generating sound. Sounds.
Yes, in fact, that's a general technique. One can start from composing from scratch, and the other thing is to take given composition, AC/DC, whatever, and then just apply some modifications where the code is wrong. That's another approach. Okay. Yeah, but I thought about it. Yeah. Okay, anything else? Anything more? Time. Okay, thank you.